All right, so in this problem, again, we're writing equations for shear force and bending moment as a function of x. And I haven't written it here, but I'll go ahead and indicate which direction we'll do x, from left to right. Really, unless indicated otherwise, I'm always going to assume we're going to go from left to right. You could choose a different origin if you'd like. Sometimes it's convenient. But just be careful and keep track of that. So as we talked about in previous problems, and we'll talk about here again, I have a continuous load over the first 12 feet, so I can write an equation for that section from 0 to 12, and then a different load from 12 to 20. So the first thing I want to kind of show you is that we would make a cut somewhere here between 0 and 12, and now you have to decide whether you want to work the left side or the right side. And then you would make a second cut. I'll call that AA. I'll make another cut over here. I'll call BB. And now for this range from 12 to 20, you want to work the whole left side or the whole right side. I think in that scenario, you can see that the right side is going to be a little easier to deal with than the left side. Over here at AA, whether you want to go left or right, I don't really see a tremendous advantage. There's going to be challenges either way. Just to show you a couple different looks, for this one at AA, I'll go to the left, and for BB, I'll go to the right. So for this section AA, looking to the left, I'm going to need to know my reactions. So I'll assume that I have a positive shear force at A and a positive bending moment at A. And I'll have to find those reactions for this whole structure. Also, I'm going to need to probably turn this into a concentrated equivalent. It's a rectangle, so that's easy. It's just base times height. So that'll give me a concentrated equivalent force of 12 times 4, or 48. And it'll happen right in the middle. So that'll be 6 feet or 6 feet. So I'm going to find my reactions first. So we'll sum moments about A. That'll eliminate the shear force at A, and I'll be able to find the bending moment at A in terms of the applied forces. I'm going to assume right-hand rule for my sign convention. So starting here on the left side, my bending moment is a negative bending moment. Is a negative moment, not a bending moment. It's a positive bending moment. I'm assuming it's negative for my accounting. The 48 will also be negative. So I have 48 kips times its moment arm, which is 6 feet. And then this guy out here at the very end on the free end, that's also going to create a negative moment. The force is 20 kips, and the distance is also 20. So when I solve for the moment at A, it looks like I get a negative value. And I don't know what that is off the top of my head. That's 400, and that's nearly 300. 688, I'm guessing. Anybody get an answer? 688? Oh, that's a good guess. 688, and that'll be kip feet. It came out negative, and I think that's reasonable. I think you can see with this cantilever beam and all these gravity loads that it's going to bend down, concave down. That's negative moment. Let's finish and get my shear force. So I sum forces in the y direction. My shear force is up, positive force. My 48 is down, and the 20 is down. So it looks like the shear at A is 68. So I have everything I need here on the left side. So what I'm going to do now is make sure that we keep all this straight, is I'm going to say, hey, I'm going to write a set of equations that are good between 0 and 12. That's this section right here. So I'm going to draw a free body diagram of that section. It's at some distance x. I have the distributed load. That's 4 kips per foot. I have my positive shear force at A. That's 68 kips. I have my bending moment, which is in this direction, and that's 688 kip feet. And then here at the cut section, I'm going to assume positive shear force and positive bending moment. So to be able to handle this distributed load, I'm going to take the concentrated equivalent of that. So it's a rectangle. Every rectangle is base times height. So base is x, height is 4. So this will be a value of 4x. And the distance from the cut to the centroid is half the distance. The distance is x, so this will be x over 2 will be the distance. I think I've got everything I need now. I can just put everything in equilibrium. So we'll start with the moment equation. So I'll some moments at the cut, make sure it's equal to 0. This moment with my sign convention is a positive moment. The 4x force about the cut is also creating positive moment. So I have a force of 4x and a moment arm of x over 2. So just to remind you, that's the force, that's the distance. And I get all the way down here to the 68. That's creating negative moment times a distance of x. And then I've got the moment here on the end, which according to my sign convention is positive. So I just solve for moment. So my moment as a function of x will now be, I'll just take all these terms, throw them to the other side of the equation. So starting here, that's 2x squared, so that'll be negative 2x squared plus 68x minus 688. And all those terms will have the units of kip feet. So there's my moment. Can I check that with anything? Do I know the moment anywhere? What is the moment at x equal 0? What's that moment right there? Positive or negative bending moment? That's a negative bending moment. Does my equation give me that value when x is equal to 0? Yes, it does. Unique to a cantilever, I've got this free end. What's the moment at the free end? In this case, it's 0. Does my equation give me 0 when x is equal to 20? You have to check that for me. I'm hoping it is. Anybody get that? Mr. Penn, are you calculating it or are you playing Tappy Bird? I'm calculating it. Okay, good man. Did I just date myself by saying Tappy Bird? Are you guys familiar with Tappy Bird? Flappy Bird? I don't care. Tappy, Flappy, Wacky.
Oh, you're saying, oh yeah, that's the new one, I guess.
It's ancient. Maybe you're playing the new version, Flappy Bird. I played Tappy Bird. What'd you get, Mr. Penn? Did you get 0?
I'm getting 0.
No, that's not good. You didn't get 0 either? Did we screw up? Maybe I screwed up here. Let's see. X squared, 2x squared, negative, positive. You didn't get 0 at x equal 20?
Got negative 128.
128? We screwed something up then. Oh, no we didn't. What did we screw up? X is equal to 20. What's the range of our equation?
To 12.
It's not valid at 20. Oh. A serendipitous lesson. You can't ask for things that are out of range. It doesn't work. I don't know if I planned that. Did I plan that? I don't know. All right, let's finish this. So let's sum forces in the y direction. So what do we get? Well, I've got my shear force acting down. Got my concentrated equivalent is also down, 4x. And my 68 kip is up. So it looks like if I solve for shear, I'm going to get minus 4x plus 68. And that's units of kips. From our lesson we already learned, I can only check shear in this range 0 to 12. I only know the shear at one point. I know that the shear at x equals 0 is 68. Is that true when I plug in x equals 0? It is. We also have our anecdotal check that the moment, the derivative of the moment with respect to x should be equal to the shear. Is that true? If you take the derivative of the moment, do you get the shear equation? You do. So that should make you feel somewhat comfortable that we've got half the problem. Okay? So now let's look at the other side. So this would be an equation that's good from 12 to 20. We talked previously about this section BB. I'm going to look at the right-hand side. So when I make my cut and look at the right-hand side, remember I'm cutting it at a distance x. So what's this little piece? What's the length of this segment here? The right-hand side. What would it be 20 minus x? If you add these two together anywhere in the beam, you always get 20, 20, 20, 20. The length of the beam has to be 20. So I have my applied load at the free end, which is 20 kips. And then I'm going to assume positive shear force, positive bending moment. I think you can see that this free body diagram is going to be a lot easier to deal with than this one. So there's really an advantage to go to the right here in this second section. So let's begin that section. So again, I'll sum moments at the cut. Make sure I'm in equilibrium. So what kind of moment is this with right-hand rule? Positive or negative? It is negative. And about the cut, this 20 kip force also creates negative moment. So it'll be 20 kips, and what's the moment arm? 20 minus x. So when I solve for the moment as a function of x, I get, let's see, I'll just write it this way, negative 20 minus x, and that all has the units of kip feet. Now looking at this part of the structure, the right-hand side, do I know the moment anywhere in that structure? Think about the one we messed up the first time. I do know the moment. What's the moment at free end? 0. So that means the moment at x equal 20 should be 0. And if you put in x equal 20, what do you get? You get 0. That's cool. If we go ahead then now and sum all of our forces in the y direction, make sure that's in equilibrium, we see that the shear force is up, positive, the applied force is down, negative. So it looks like the shear as a function of x is simply just 20 kips. It's constant. One thing we can think about is the derivative relationship. So is the derivative of the moment with respect to x, is that equal to the shear for this second section? Yes, it is. Well, that's comforting. Now, do I know something about the shear? Well, you have to do a little investigation to see what's going on here. If I cut just a little teeny tiny chunk of the beam, such that on the right-hand side was 20 kips, and on the left-hand side was positive shear. See that? That's just right up. That's as close as you can get to B without being underneath it. What's the shear equal to? 20. So we do know that the shear at x equal 20 should be 20, and not hard to see that our function matches that. There's one other thing you can do, is you can check the moment from the first section with the moment at the second section with the one point they have in common, which is what? This one ends at 12, this one starts at 12. So I'll squeeze it down here, you can barely see it. And I'll come back and call this 1 and 2. So, does the moment from 1 at x equal 12 equal the moment from 2 at x equal 12? Take you a little longer to do. This one I can do in my head. If I put 12 in there, I get 8. 8 times that's negative 160. Does this one also give you negative 160 at x equal 12? A little harder to do. Yep. There you go. So that works. So there's a lot of things you can check along the way to kind of verify that things are going well. Now, this problem took us 18 minutes to do with all of our talking and missteps. So again, this is a doable problem for the exam. Any questions?